th2 is an open-source, next-generation test automation framework for financial markets. It's designed to enable automation in functional and non-functional testing for complex distributed transaction processing systems. The key features of th2 are a high level of customization for financial systems. It has a library of existing built-in test components that supports multiple protocols, such as FIX and its dialects, native, SIP and TCP, etc. And it allows you to create custom components to support the logic that's specific to your financial system. th2 allows you to develop your test components using mainstream programming languages such as Java, Kotlin, Python, and C++. th2 uses unified data storage that enables you to bring AI and ML into testing. It also provides you with various options for testing, such as real-time based automation, model-based testing, load generation, and more. Today, we'll tell you about th2 and its integration with FIX Orchestra. FIX Orchestra aims to provide a standard for machine-readable rules of engagement between counterparties. Its goal is to reduce the time it takes to get counterparties trading and improve the accuracy of implementations. It contains additional information that's not provided in the commonly used libraries for implementing communication using FIX protocol, such as QuickFixJ. You can specify conditionally required fields for messages, different sets of tags in messages for different scenarios of message use, and many other rules and validations. Today, we'll see how this allows you to perform additional validation during functional testing. In the demo example, we'll execute the following scenarios: sending a valid limit order, sending a valid stop order and receiving an invalid execution report, and sending an invalid stop limit order. We will emulate system behavior using the th2 sim component. It allows you to define the rules that will generate a response for certain requests. Let's take a look at the rule definition. We can see that the rule takes a set of fields from the original message, adds some additional fields to the response, and sends it back. Note that the stop_px field is not copied from the original message. Let's run our scenarios using the base FIX codec that does not know anything about FIX Orchestra. As we can see, everything is green after the execution, and no errors were generated by the codec. Let's take a close look at the generated events. We can see in the second scenario that the execution report does not have a stop_px field, but it was still accepted by our script. In the third case, we can see that we were allowed to send a message without the required tag, and we have received a business message reject message. For that run, we were using the codec that uses the QuickFixJ library for decoding and encoding messages. Now let's switch to the FIX Orchestra codec. It can work in two modes. The first mode is the error mode. In this mode, the codec reports an error and does not allow the message to go further. The second mode is the warning mode. In this mode, the codec reports a warning, but the message still goes further in the chain of components. Let's start with the error mode. Let's run this script again. We can see that the output is different now. Let's go to the report. We can see that the report now contains failed events in our scenarios, and the codec root event also contains events with errors. Let's take a closer look at the second scenario. Now we see that the invalid response was not received by our script. The codec contains an event about the error that occurred during message decoding. We can see that the required tag 99 is missing. Also, in ACT events, we can see the list of messages that were processed by ACT while it was trying to find a response. Our execution report with the error reason is one of them. In the third scenario, we see that the message was not sent at all. The codec has blocked it from going further. It can be used to stop testers from sending messages that do not correspond to the specification in positive scenarios. Now, let's switch to the warning mode and rerun our scripts. At this time, all the events are green and our scenarios are passed. But let's check the codec events. We can now see warnings among those events. They say that something has happened during the codec's work. Here, we can see two warnings, one for the invalid execution report response, and one for the invalid new order single request. Also, we can see a reference to a warning in the codec in our third case, where we had sent an invalid request. Because th2 uses a unified storage for all test data, we can also analyze the results after the fact, using th2 data services. It's a Python library that allows you to request data from that storage and perform different operations on it. You can aggregate data, collect links between messages and events related to those messages, as well as build charts and tables based on that data. For the purposes of the demo, we will extract all the errors produced by the FIX Orchestra codec and see which messages it affects and what kinds of errors we get when running our scripts. This brings us to the end of our demo of th2 and its integration with FIX Orchestra. Thank you for watching.